Howdy everyone. My name is Sure Bandari, Technical Director at ASCE Dallas branch. Today we have Transportation and Development Institute Technical Session Speaker Parameshwar Ankam, PE, is a Senior Project Engineer at Parsons Research and Office. He has more than 16 years of experience in highway, traffic design, and 3D modeling. His experience includes design of roadway geometry, complex interchanges, intersections, and street improvements, bus, rapid transit facilities, light rail improvements, sidewalks, driveways, and parking lots. In the past 7 to 10 years, he has been heavily involved in developing detailed 3D models. He performed detailed grading of various civil design elements and produced detailed machine gradable DTM surfaces for construction of various roadway projects. Parameshwar graduated from University of New Mexico in May of 2004 with Master of Science in Civil Engineering with Transportation as major. He has obtained a great deal of experience on many design build projects in Texas. Let's welcome Parameshwar Ankam PE to our Transportation and Development Institute speaker session today. Thank you.
First of all, I would like to thank ASCE committee for giving the opportunity to present. And I will be presenting my topic today on design validation using 3D modeling. And let me share my screen and then let's get into the topic. Okay, so I will be presenting my topic on design validation using 3D modeling, and I will be discussing how important it is to develop a good 3D model and how important 3D models are for the success of any transportation and civil infrastructure projects. And let's look at the agenda items for the presentation today. And I will be talking about various benefits of 3D modeling and design validation, like how to validate the design using the 3D model software. And I will be discussing about some of the design errors and omissions and any issues that we can identify during the modeling process. And then I will also be talking about how to QC the model and then how to review the model for the quality and accuracy purposes. And I will be talking about the final products of 3D model and what all the files that 3D model can generate. And I will be sharing some of the testimonials from the field. And I will be also talking about some of the current modeling practices in the transportation industry, and I'll be talking about some of the challenges with this automation. And I will be talking about more on the ORD side, and then I'll be sharing our experience on the ORD software, and then how powerful ORD can be to automate the design and also to develop automated 3D models. And I will be discussing about the open roads designer usage at Parsons later on. And these are the benefits of 3D modeling. And as you can see, there are many benefits with the 3D modeling. And mainly the 3D model helps visualize any solution. Like sometimes the solution might be very simple or complex, but it gets very hard to explain and then convince the client sometimes. So that's when the 3D model comes into picture, and then to help visualize that solution and then convince the client the design solution would work. And then I'll be discussing about, we're going to go over these in detail, and I'll be giving examples for these different benefits. So 3D model produces various roadside design conditions. So at Parsons, we have developed intelligent grading templates that are programmed to incorporate various text roadside design conditions to optimize the roadside design based on the right-of-way availability and then other roadside conditions. And I'll be discussing about some of the benefits that we can catch the design errors during the design process during modeling. And then I will be also discussing about the benefits of 3D model, how it can help validate the ultimate designs. And then we will be looking at some of the quantities that 3D model can generate, and 3D model also helps with producing mass hall diagrams. These are extremely helpful for the contractor to see the dirt availability at any given location all along the project. And it also gives a good idea for the contractor to check for their hauling requirements. And we will be looking at the final outcomes from the 3D model and different files that 3D model can produce, and how they would help for other designers and disciplines to do their design and optimize their design. And nowadays, many contractors use machine control grading in the field, and they will be requiring us to provide the 3D break lines and land XML files, and these would be very compatible for their machine control grading, and especially with Trimble Business Center and Actec, those softwares can read the DTMs and land XML files and 3D break lines. And then I'll be talking about the potential utility conflicts that can be identified with the help of 3D model, and then we will look at some of the floodplain impacts that can be identified with the help of 3D model. So like I just mentioned, no matter how simple or complex the design solution might be, and sometimes it's very hard to explain on a piece of paper. So that's when 3D model becomes extremely helpful. So in this example, based on one of the previous project experience, the client and the reviewer wanted to see how our interim design of these walls would work for the ultimate condition. They wanted to verify that these walls would work for the ultimate condition as well. So in this slide, you can see there is an ultimate ramp, and you can see there is an interim wall that got generated right next to the ramp, and then the mainline wall was terminated in a certain way with a full height that would match for the ultimate condition, but in the interim condition the wall was terminated with the interim grading, with that conic grading that you can see. And when we presented this to the client, and they were able to visualize our solution, and they got convinced, and then we were able to move forward with our design. So this is how 3D modeling helps validate the interim design would work, and it would still accommodate the ultimate conditions. So here is another example. This is one of the intersections where the cross street had future U-turns, and we had graded these U-turns in the interim condition using the ultimate U-turn profiles. And we were able to accurately grade those areas to make sure that there are no drainage issues in the interim condition. And also we were able to produce the finish grade and bottom of walls for these abutment walls accurately based on the ultimate condition, and also they would work for the interim as well. This is another location where we had a cross street in the future, but we had to grade this area for the interim condition to make sure that there would not be any drainage issues and ponding issues. And we graded this area in such a way that all the water would drain to the nearest culverts. And then as you can see in the profile view, that we were able to generate and extract some features to set the interim finish grade and bottom of walls, and they would work for the ultimate condition as well. So this is another location where we had a cross street that we had to grade the U-turns for the ultimate condition. We just needed to accommodate the U-turn design in our interim condition, and so we had to grade those U-turn areas and then set the bottom of walls and finish grades correctly, considering those ultimate U-turns. And based on the ultimate U-turn profiles, we were able to grade those areas correctly. And then later on in the project, TxDOT wanted to add the U-turns, and then we were able to incorporate those U-turns very easily with minimal impacts to the retaining wall design, and then the drainage design as well. As you can see, the 3D model that we developed, that worked out pretty good. This is another location here in Dallas. We were able to produce a detailed 3D model considering and then accommodating the future U-turns. This cross street that's crossing over the main line had future U-turns, so we had to set the top of walls correctly to accommodate the future U-turn bridge deck and based on the structure depth for the future U-turns. And then there were these left turn pockets also. We had to accommodate the future walls. So, and this is another benefit with the help of 3D modeling tools. We can accurately compute the earthwork quantities, and there are various earthwork quantities that we can produce from the 3D model in addition to the regular embankment and excavation quantities. We can also estimate and compute various select backfill material quantities as well. And then we can also estimate the quantities for topsoil and pavement quantities and different other earthwork quantities. And with the help of the new ORD and open road technology, we can run the dynamic section. This is an excellent tool that you can run the dynamic section anywhere along the project to see if there are any potential conflicts. So based on the plan view information, if you see any conflict and you want to know more detailed conflicting information, so you can cut a dynamic section at that location, and then you can easily identify and then accurately identify that conflict in the cross-section, dynamic cross-section view. And as you can see in this picture, there was a gas line that was in conflict with the drill shaft for the noise wall. And then we were able to adjust the spacing of the drill shafts to avoid this conflict. So there is one recommendation here: if there are any noise walls or CAP walls being designed, then it's very important to lay out the drill shafts on the plan view so we can check for any potential conflict with the underground utilities, especially and also with the drainage. So this is another example where we were able to catch one of the drainage pipe conflict. This was an asphalt pavement, and then we had an SSTR right next to the roadway. And then usually these SSTRs that are placed next to the asphalt pavement would require a TRF foundation, and the foundations are 2 foot 9 inch deep. And then when we were checking and doing the clash detection analysis, we were able to catch that there was a drainage pipe running underneath the barrier, and the foundation was in conflict with the drainage pipe. And then later we brought this to the attention of the drainage engineer, and then they were able to resolve this issue. So this is another benefit with the 3D model. We can easily identify the impacts to the floodplain areas. And we can also estimate the quantities and the volumes of floodplain impacts. So using advanced terrain model techniques by producing clipped terrain models and complex terrain models, we can easily estimate, and we can accurately estimate the volume of impact in the floodplain areas. And then also we can look for the potential sources of mitigation in the project vicinity. And then we can also optimize the ditch profiles and then generate an additional mitigation in the floodplain areas. So these are some of the topics that I will be covering as part of the design validation. So with the help of 3D modeling tools, we can check profile tie-in issues. We can identify and verify any potential design errors in the intersection design and grading. And we can also validate the slope riprap limits and then optimize the riprap limits at the bridge abutment areas. And then we can also look at some of the design, how we can identify the design errors during the modeling process. So I can show some of the examples for these design validation here. And we can also check for any potential ponding areas in the intersection. And then we can also optimize the culvert design, the culvert length and head wall length, and then we can also optimize the geometry of the flared wing walls for the culverts. And like I mentioned earlier, with the help of intelligent grading templates, we can optimize the retaining walls and side slopes, barriers, and also minimize the concrete riprap areas. And we can also look at some of the abutment wall geometry. We can review them with the help of 3D modeling tools by developing detailed abutment wall models. We can validate if the abutment wall layout would work or not. And you can see one of the benefits, and many times during the proposal phase, we develop quick ATC design solutions. We can come up with alternative designs, and with the help of 3D modeling tools, we can quickly develop the 3D model and then also generate the quantities at the same time for cost comparison purposes. And then we can also identify the utilities as we just saw. And this is an example in one of the previous projects. During the design process, we were able to identify some of the profile tying issues. As you can see in this picture, the ramp was not tying correctly with the main line and it was higher. And then we brought this issue to the attention of the designer, and then later they were able to resolve this issue, and then they redesigned the profile and they fixed the profile. And then as you can see, the profile tied in perfectly at the physical core with the main line. And then later we were able to validate their design. So this is another example for the profile tie-in issue. So in this example here, the profile was extending beyond the physical core here, and not only that, and it was much higher at the physical core at the tie-in point. So we brought this again to the attention of the designer, and then they were able to fix the profile, and then that's how it looks after the profile was fixed, and we were able to resolve this issue and validate their design. Intersection tie-in issue. So this is on one of the previous projects when we developed the preliminary model based on the intersection detail plans provided to us based on the cross slope information and intersection tie-in elevations. We were able to incorporate that into the model, and then later we found some issues at the ADA ramps, and some of the corridors and some of the ADA ramps were not tying correctly, and then there were some issues, as you can see in this clouded areas. The contours are not smooth, and there were some tying issues here. And then we coordinated with the design team, and then we were able to resolve those issues by tying, by suggesting alternative elevations and cross slope transitions. And then in this picture, as you can see, the smooth contours that explain how those intersection tie-in issues were resolved. And in this picture, you can see there is no ponding issues around the ADA ramps, and we were able to verify the crosswalk cross slopes would also work for, and then they would comply with the ADA requirements. So based on some of the previous project experience, we've been developing very detailed intersection models, and we are accurately incorporating the curb return profiles and cross slope transitions in the model. And this is how we were able to ensure that all these corridors tie in correctly. So in this picture, as you can see in these 4 yellow circles, there were different corridors that are tying to the cross street, and they would all tie correctly. And then when we produce the contours, and this is how the contours turned out to be. So the contours are extremely very important to verify and check the intersection design worked out good. And as you can see, when in this top picture with the dark blue contours, during our modeling QC, sometimes some of the 3D features and 3D break lines might not get triangulated correctly in the terrain model, and they would produce incorrect contours. And then we were able to catch this during the QC process, and then later on we were able to resolve that issue. And then so in this pink contours, you can see everything worked out pretty good, and the break lines were triangulated correctly, and then the bottom of wall and the finish grades were generated correctly in the 3D. So this is another intersection where the intersection had a very severe skewed geometry. So as you can see in this picture, the cross street had a very severe skew, and then it was tying with the frontage road, and there was a driveway here, and we were able to accurately incorporate the curb return profiles, and then also accurately able to incorporate the crosslope transitions through this intersection, and then made sure that all the corridors tied in correctly, and then there are no tying issues identified. And then when we produced the contours, this is how the contours turned out to be. So this kind of validates the intersection detail design. So using the 3D model and then the 3D modeling tools, we can optimize and validate the sloped concrete riprap limits around the bridge abutments. So as you can see in this picture, the dark circle here, that was the layout designed for the riprap limits by the designer. And then when we developed the detailed 3D model for this abutment slope riprap, we were able to identify that the limit was too short and it was not tying correctly with the ditch flow line. And then as you can see in this 3D picture, the riprap limits were later optimized, and then the toe of riprap tied correctly with the ditch flow line here. And that kind of validated and optimized the slope riprap limits. So we were also able to check and then verify the maximum slope criteria was met under the bridge and all along the slope riprap by running the dynamic section to make sure that the slopes are complying with the design criteria. So this is another location where the concrete riprap limits were optimized, and then the toe of riprap was tying correctly with the ditch flow line. And then with the help of 3D modeling tools, we were also able to optimize the bridge wing wall lengths. As you can see in this right picture, many times the designers would come up with the wing wall lengths based on the structure depth and also 1 foot below from the top of cap, and then come up with their length. But sometimes they might ignore the fact that the roadway might be on a grade. So with the help of 3D modeling tools, we can accurately estimate the wing wall lengths by considering the roadway grade as well. So this is another location, another slide that explains that we were able to identify the vertical conflict of the culvert with the roadway. And we brought this issue to the attention of the designer, and then later they were able to raise the profile, and then that issue was resolved. As you can see in this 3D picture, when we had this vertical conflict, the culvert was exposed and it was embedding into the pavement area. So in this slide, it kind of explains and demonstrates that the detailed intersection designs and the display of contours kind of validate the intersection design. So in this picture, we have used the drainage drainage trickle tool to verify that there is no ponding anywhere in the intersection area, and then also especially around the ADA ramp. So oftentimes the designers might not check any flat spots and ponding areas occurring around the ADA ramps, and then we need to set these ADA ramps in a flat spot, and we also have to be cognizant that there would not be any low spot that gets created in those areas. And so as you can see, these are the flow arrows developed and then drawn using the trickle tool, and then that validates that when the water drops here, then that would drain away from these ADA ramps. So this is the intersection, and that's the 3D model view of that intersection. So this is another a good example that 3D model validates the abutment wall layout. So during on this project during the early design stage, the retaining walls were curved, and then later on the contractor wanted to bend in a certain way, and that is mainly for constructability reasons. And then when we incorporated that into our model, we noticed that that created these humps, since the horizontal distance get reduced to spread that vertical drop in the radial direction here. And then that was creating resulting in these humps, and then resulting in the low spots occurring right next to the bridge abutment caps. And then later on, we were, with the help of advanced grading tools, we were able to eliminate these humps, and then also make sure that there are no low spots occurring around these bridge abutment caps. And we were able to optimize the concrete riprap limits, and also were able to verify the maximum slope criteria was met. So in this picture that you can see the pink contours, with the help of detailed grading tools, that kind of demonstrates that how that those humps were created, and then how the low spot was getting created. So this is in this slide, I'm going to go over some of the important steps that have to be considered during the design phase, especially during the early design phase. So especially when there are MSC walls and head walls that would have interaction. So the controls have to be set correctly. So the MSC wall control and the head wall controls have to be laid out correctly on the plan view. Such that they would not result in any issues. And during the early design stage, we were able to identify in one of the locations that the culvert was sticking out, and it was protruding beyond the MSC wall. As you can see, the head wall was sticking outside the MSC wall. And in the dynamic section also, you can see how the head wall was sticking out. And then later we brought this to the attention of the drainage engineer, and then and we were also able to provide the optimized culvert length and the location. We were also able to suggest the accurate location of the head wall, and then that issue got resolved. And as you can see in this picture, it shows how the head wall got moved, and then the culvert length was optimized. So in this slide, you can see in one of the locations, the original plan was to salvage the existing culvert and do not disturb that culvert. And then when we were developing the detailed grading around this area, there was a proposed driveway, and then we were checking the slopes, and then we noticed that the existing slopes were pretty steep, and they were one-to-one, and they were not complying with the design criteria for this project. And later on, we brought this to the attention of the drainage engineer and other contractors' attention. And then we also looked at some of the field pictures for the existing culvert, and the culvert was in not in a good condition. And then we developed this detailed grading, and then we were able to suggest the upgrade and then improvements to the head wall, and we were able to replace these head walls, and we were able to provide the accurate geometry for these head walls, and develop a detailed grading to make sure that that grading would work. This is another location based on the accurate control set for the MSC walls and culvert head walls. We were able to make sure that the head wall would line up with the MSC walls, and they would all tie in correctly, and we were also able to optimize the head wall in this area. This is another location I would strongly encourage for all the designers to thoroughly check the ditch profile design to make sure that they would work for the culvert design. And in this picture, you can see that the ditch profile provided was not matching with the culvert flow line. And then we were able to bring this to the attention of the drainage engineer, and then they were able to revise the ditch profile, and later that issue got resolved. As you can see in the picture on the right, that shows the issue got resolved by optimizing the ditch profile. This is one of the areas where we were able to identify the steep slopes due to the right-of-way constraint. And the cyan line shown here was producing very steep slope that was 52%, and it was not complying with the slope criteria for the project. And then later on we were able to suggest the acceptable side slope in front of the culvert downstream end, and then we were also able to provide the amount of additional right-of-way needed based on the 3D modeling techniques. So in this picture, with the help of terrain models, we can easily identify the impacts in the floodplain areas, and then we can also estimate the amount of floodplain volume impact, and then also we can estimate the mitigation volume in the project vicinity. So I'm going to talk about some of the QC modeling tools. So if we were able to QC the model accurately based on some of the steps that I'm going to talk about here to check the quality and accuracy of the model. So it is always important to check the modeling alignments. They would match with the roadway alignment that were designed. And every single ramp and cross street and frontage road and mainline alignments from the modeling side would also match with the roadway design. So they would all have to line up with each other. And then we would also have to check the payment model payment edge file and overlay that with the roadway edge file to make sure that they all align correctly, and then they would all match. So, and then this is another tool that based on the final product, the 3D model produces a terrain model. So you can overlay the terrain model on the design roadway profile to make sure that the model surface follows the roadway design roadway profile. So it's extremely important that there has to be good communication between the design and modeling team. So when there is any design change, that has to be thoroughly communicated with the modeling team to make sure that that gets incorporated correctly in the model. And then it's always a good idea to display the contours once the terrain model gets created from the model. It's always a good idea to generate the contours and then review the contours thoroughly. And then, so we would also have to check the contours to make sure that the low spots and then the inlet locations would match. So, and then also the culvert would line up correctly with the contours. So with the help of 3D model contours, we can look at intersection contours to make sure that there are no ponding issues and no cross slope issues and no tie-in issues at the intersection. So this is another tool that ORD and Bentley is coming up with, the digital twin. So we can review the live model, and then we can tag the error point, the error location, and then that would send an email to the designer, and then that would send an email and then would pop up to the design team. So based on the thorough QC of the model, and then we made sure that all the 3D break lines are triangulated correctly. And then sometimes the 3D model look really nice, but when you look at the contours, you might see issues with the contours, and some of the finish grade features of the walls are not triangulated correctly, and those kind of issues can be easily seen in the contour grading. So as you can see in this picture, we were the 3D model very closely matches with the contour as well. So this is another intersection where we did the detailed, we developed the detailed intersection model, and then the contours on the right would match accurately with that model. So this kind of gives confidence to the contractor and reviewer that the quality of the model. So these are some of the field pictures that we received. So this is a model that we developed for a project here in Dallas 3 years prior to the construction, and then we developed a very detailed model for this project, and then this is how it looks after the project was constructed. So as you can see in this intersection, this was a very severely skewed intersection, and it had too many ADA ramps and crosswalks and truck turning movement, and we were able to grade all these areas accurately in the 3D model, and the contractor used the machine control grading on this project. This is another location that I pointed out earlier, that we were able to set the top of walls correctly, considering the ultimate U-turn design. And then this was the model developed 3 years prior to the construction, and this is how it looks after the construction. So it closely matches with the 3D model that we envisioned and we developed. So this is for another location, for another project that we developed a detailed 3D model for this area. And then this is a field picture after the project was constructed. And then as you can see, this can clearly depict that the after construction picture closely matches with our detailed 3D model that we developed 3 years before. This is another location for one of the intersection that we developed a very detailed 3D model. As you can see, we modeled all the traffic signals, area ramps, street lighting, and we provided 3D striping, and we pretty much modeled everything for this area. And then this is how it looks after the construction. So I'm going to be talking about some of the current modeling practices in the industry. So presently there are still many designers that are using the old inroads tools and geopack tools, and there are some challenges with those design tools, that they don't have the ability to update the models and update the design automatically, and they have some challenges with automation. So with the help of ORD and open road technology, and that's a very powerful software, and it helps with automating the design. So all the roadway geometry is laid out with reference to an alignment with a civil geometry alignment, and then the ramp geometry and the ramp tapers and the shoulders and the cross streets and the merging, diverging locations and the core areas, they were all drawn with the help of in reference to baseline alignment. And when the alignment changes, all the ramp geometry that were laid out in reference to the alignment with those rules, they would also change with it. And then it is very powerful and very dynamic. So as the alignment changes, all the ramp layout and the taper lengths and the shoulder widths, and they all get updated automatically with the rules that were set ahead. And then there are some good tools with the ORD that we can automate the routine 3D modeling process. We can develop some 3D civil cells that would automate and quickly develop the 3D solutions for driveways and intersections, and sometimes the complex intersections. So with the ORD, like I just mentioned, the civil geometry can be automated, and then when any alignment changes, the pavement information changes, the pavement edges changes, so that design, the 2D geometry changes, and then with that help, that information gets referenced into the 3D model, and then the model gets updated automatically when the design changes occur. So that helps with the 3D modeling automation process, and the models become very interactive. So when the model gets updated, the cross sections get updated, and the terrain model gets updated at the same time, and then we can update the contours at the same time. So everything gets synced with those design changes. So I'm going to present one of the simple intersection civil cell that we developed here at Parsons. I'm going to share how that civil cell design works. Yeah, in this video, I'm going to present how this simple intersection civil cell works. So there are two cross streets here with alignment, and then the civil cell that I'm going to put is simple intersection. And then I just picked two cross street alignments, and I'm going to check highlight those two alignments, and then it's going to produce a 3D model of that intersection. There you go. So as you can see on the right side window, the 3D model is produced with just 2 clicks. Previously, it used to take at least a day or so to develop these detailed intersection models. And now that information, the 3D model can be developed very easily with just few clicks. And then this information can be modified at any time after the cell is placed. You can change the width of the roadway, you can change the width of the sidewalk, you can change the radii information uh, to fit the custom needs, and then I'm going to show here how powerful this civil cell is. When the alignment changes, 3D model gets updated as well, and the sections get updated, and the ETM terrain model gets updated at the same time. So you can update models at the same time. It is so that so and it's so very interesting. I'm going to show another civil cell that we developed here at Parsons. This is a complicated intersection, and I'm going to show how the civil cell works. This is a civil cell for a diamond intersection, and it is a little bit complicated intersection civil cell. And with just few clicks, it can develop a very detailed intersection model for a diamond intersection. And this civil cell uh, generates a 3D model for half of the diamond intersection, and then the same cell can be used to develop the other half of the intersection. So in this cell, civil cell, it has 3 steps. So it has the you have to pick the pass slope, the pass street alignment, and then the first part of the frontage road alignment, and second part frontage road alignment, and then it can generate the 3D model very quickly. There we go. So as you can see on the right side window, it generated the detailed 3D model for the diamond intersection. And as you can see in this 3D, it generated it generated a detailed model of the U-turn and raised median islands, and as you can see, everything ties in perfectly. And the cell is programmed to behave in a certain way that it will work with all other designs. So you can change the width of the roadway, you can change the radii information, and as you can see, it can generate the side slope rating as well. And then you can change any information after the cell is placed, and then you can change the alignment as well, and then it gets updated automatically, and it is so powerful and interactive. So as I'm demonstrating here, I'm changing and modifying the alignment, and then the model gets updated automatically. This type of model, to develop a detailed model, used to take at least 3 to 4 days before. But now with this civil cell design that we developed at Parsons, we can quickly generate this 3D model with just a few clicks, and then we can customize it later on. So I'm going to discuss some of the ORD practice here at Parsons. We've been heavily using the open source designer software since last 2 years at Parsons, and we've been the major user of Bentley ORD software on many major design build projects here at Parsons. And we've been providing training on the ORD software to many textile districts, and there have been a good turnout on these training sessions, and we're here to help to provide any training if anybody needs any training. And yeah, like I just mentioned, we were able to provide good training on these latest ORD software to textile district, and the ORD is so powerful that it can not only just automate the design, but it can also produce the plans, and then the plan production can also be automated, and then when any design changes occur, the plan and profile sheets get updated as well. And thank you for the presentation, and then you all stay safe. Thank you very much.